I've brought up this word failure several times up to this point. In fact, it's in our definition for reliability. So what is a failure? Definitions of failure often depend on their context. We can either fail to perform an event or fail to comply with design's intent. We can define an event failure as an event or a situation in which a system or any of its internal components does not or would not perform as specified in the system requirement specification. Failure events can happen in one of two ways. The first is it can be a premature system or entity failure caused by a fault or a failure of some external system. For example, a component in your vehicle's engine fails prematurely due to a failure by the user to do something like change the oil as recommended by the OEM. The second failure event can be a failure that occurs because some internal breakage due to wear, tear, fatigue, corrosion, or fractures. A conditional failure is a failure where a system or an entity performs poorly or is in some degraded state or deteriorated to where it's not compliant with its specification. A failure condition is time-dependent and a consequence of a fault that's occurred. A fault represents a hazard that, if something is not done about it, might become a failure and might contribute to an incident or an accident. Several factors can cause a fault to turn into a failure. Defects in the makeup of a component, like the material it's composed of, might have some flaws, like air voids in the metal or the plastic. That's just one example. Or perhaps there's design defects where the design itself is flawed, or a component that was not manufactured properly, either through following a flawed assembly process or deviating from a satisfactory assembly process. Or maybe the user's not operating the product or the component properly. We see this more often than not. And I'm sure you've experienced it yourself, where your product just isn't doing the thing that you need it to do, and then you actually read the manual and find out you've been using it wrong. Hopefully it didn't break, but ultimately you discover how to work the product correctly. Another cause for failure might be a lack of maintaining a product. For example, if you don't change the oil in your car at the suggested intervals, then don't be surprised if the engine seizes and you need to get your engine overhauled. Or if you leave batteries in an electronic device that rarely gets used, don't be surprised if you return to it much later and the batteries have leaked acid all over the circuitry, ruining the device. So change your oil and remove your batteries. As a final note, a failure can be temporary, lasting only a short time and then it goes away. It might also be intermittent, where it happens and then seems to go away and then might come back later. A failure can also be permanent. And these factors depend on the product itself or how it gets used, or if it's used in an improper or an unplanned manner. Ultimately, as a project manager, systems engineer, or chief engineer, whichever title you might go by, if you're in charge of managing a product development effort or taking part in a product development effort, your job is to agree on a common definition for what constitutes a failure in your team project, and preferably within your own organization. This definition, and the definition of all the terms that you're learning in this course, should be captured in your Systems Engineering Management Plan, or SEMP. Your organization might call this the Technical Management Plan, or might have a Project Management Plan with a technical section. The reason why you want to capture and communicate the definition of a failure across your organization is because it will minimize the tendency for your team members to rationalize away failures during tests. Academically, we can define a failure as a non-compliance with the system requirements specification. But most products don't show us the spec compliance of every component within the system. This approach would simply be impractical and cost prohibitive. Ways that we can reduce the number of failures in our system is to first monitor a few essential, mission-critical, and safety-critical components by using things like sensors or instrumentation. Second, we can perform preventive maintenance at scheduled service intervals. And third, we want to properly train the operator and maintainer to be aware of and inspect the system for strange noises, smells, unusual heat, leaks, chafed wires, or fatigue cracks. These might clue us in on potential pre-failure indications that might require corrective maintenance. Before we leave the subject of fault definitions, let's go over the importance of detecting and eliminating faults. Every single fault, if left undiscovered in a system design or its construction, is a potential risk that can jeopardize accomplishing missions, can cause injuries or loss of life to the user or the public, or can cause damage to the product or cause harm to the environment. When a product fails, it provides no value or less value to the owner or the user. With larger, more complex systems, if they're not operating, they're not producing revenue. Instead, they're consuming revenue to repairs or replace broken parts. This graphic depicts the 100-time rule, demonstrating graphically how early errors roll forward into each development phase. This implies the cost incurred toward a product development effort exponentially grows as the design and the development effort rolls along. When a fault emerges, the profitability of that product goes down. Therefore, reducing or eliminating errors or faults that can become failures has to begin early in the concept development stage of the product lifecycle. This graphic shows how important it is to reduce or eliminate defects or errors or faults early in the system development stage. During the bathtub portion of this module, I'm going to address a concept called the decreasing failures region, or the DFR. Reducing or eliminating faults early in the system development stage provides significant benefits. In the next section, I'll expand a bit on the criticality of mission success and the criticality of ensuring your product is safe in all states of operation.